Hello, Marcus.
Okay.
Hello, Greg.
So welcome everybody to this second day of conference. And as a first speaker, we have Michael Pedroni from Università di Bergamo. He will talk about Poisson, quasi-Nijenhuis manifolds and integrable systems. So please, Michael, you can start.
Okay, so many thanks to Valeriano for organizing this conference and also to Ugo for helping him. I think it's very important and also very appropriate to celebrate Claudio's 60th birthday with such an interdisciplinary event. I spent 11 years at the math department of the Genoa University, and I had the gift to meet wonderful friends there. Most of them are participating in this conference. And Claudio is certainly one of these gifts, maybe the most important one, since I had the pleasure to collaborate with him both for teaching and for research. I learned a lot during the discussions we had, not only at the math department, but also in restaurants, at his home, and several other places. And I learned a lot of mathematics, but also history, geography, philosophy, and you know much better than me that I could continue with all possible fields of knowledge. So I'm very happy for this opportunity to say once more thank you to Claudio for our friendship. And okay, now I'll try to share my screen. Okay, can you see it?
Yes.
Okay, so Claudio wrote two papers in collaboration with me. The first one was about the Neumann system, which is an example of a finite dimensional integrable system. And the second one was about the Calogero-Moser system, which is another well-known example of a finite dimensional integrable system. And in this talk, even though it is not in the title, I will spend many words about a third example of very well-known finite dimensional integrable systems, that is to say the TODA system. And the results I will talk about were obtained in collaboration with Gregorio, Igor, and Giovanni Ortenzi. And there is a first paper which was published 2 years ago, and another one that can be found in the archive. So the plan of my talk is the following. First of all, I will recall the definition of the so-called Poisson-Nijenhuis manifold. The definition is mainly due to Magri, Morosi, and Ragnisco and goes back to the 80s. And the relation between this geometrical object and, as I was saying, finite dimensional integrable systems. Then I recall an interesting generalization of Poisson-Nijenhuis manifold. It is called the Poisson quasi-Nijenhuis manifold. It was given in more recently, 15 years ago, by Stianon and Xu. And an important point is that in the Stianon-Xu paper and also in the rest of the literature, as far as we know, there are no relation with the integrable systems. Then I will describe a general procedure to deform a Poisson-Nijenhuis manifold into a Poisson quasi-Nijenhuis manifold. And then I will frame in such a geometrical structure the closed, sometimes called also periodic and particle-Toda lattice, and also its relation with the so-called open or non-periodic Toda lattice. And finally, I will present sufficient conditions on a Poisson quasi-Nijenhuis manifold such that a family of functions in involution can be easily constructed on such manifold. They will be simply the traces of the power of the recursion operator. So what is a Poisson Nijenhuis manifold? We have a manifold M, finite dimensional manifold M, a Poisson tensor pi, so in other words, M and pi form a Poisson manifold. And then we have also a 1-1 tensor field N. We will consider a 1-1 tensor field N as a map from the tangent bundle of M into itself. And these two objects, pi and N, must satisfy some requirements. The first requirement is only about N, and the requirement is that the so-called torsion of N must vanish. We will see what is the torsion in few minutes. Then there is a compatibility condition between pi and N, and I will explain in which sense they have to be compatible. Okay, first of all, I recall also what is the meaning of the word Poisson manifold or Poisson tensor. So in this talk, the tensor pi will be a map from the cotangent bundle of M to the tangent bundle, and we will say that this tensor and the manifold M is a Poisson if the composition law between C infinity functions, which is given in this way, so the Poisson, so-called Poisson bracket between F and G, is the evaluation of df on the vector field, which is simply pi acting on dg. So pi acting on dg is the so-called Hamiltonian vector field with the Hamiltonian given by G. And so the pairing between the one form df and this Hamiltonian vector field gives a new function. And if this composition law has the usual property of the Poisson bracket, I will not recall these properties now, then we will say that it is well known that pi is said to be a Poisson tensor. So the Nijenhuis torsion of N is this composition law between vector fields. X and Y are vector fields on M, and Tn of X and Y is another vector field constructed in this way. And so the requirement about N was that the torsion of N should vanish. It means that Tn of Xy should be 0 for all X and Y, for all vector fields X and Y.
Sorry, Michael, but maybe you should hide this dark bar on the bottom.
Okay, but then I think it's not visible. That's what I
Nascondi should do the job.
Yeah.
Okay.
Okay.
Sorry.
It hides everything.
Try again. Yeah, sorry, I don't know how to. I was prepared for Zoom, but not for.
Instead of interrompi, nascondi just.
Okay.
Sorry, I made things worse.
No, but you were right. So now you are not seeing my screen, I guess, right?
Right.
Okay. Let's see what I can do. Okay. Is it okay now?
Well, there is always the bar, but
yeah, but I don't know what to do with this. I'm sorry. Okay, maybe.
okay.
Now it's better.
Now
Yes,
it's
now
perfect.
it's perfect.
Okay.
Thanks.
No.
Okay, torsion.
Okay. Yeah, but now the arrows do not do not work anymore. I don't know why. Okay. Okay. Can you see now?
Yes.
Okay.
Yes.
Okay. Thank you for the improvement. So now I want to recall what is the compatibility requirement between pi and n. There is a first algebraic and very simple requirement, is that the composition between n and pi is the same as the composition between pi and n star, where n star is simply the transpose of n, which is a map from the cotangent bundle into the cotangent bundle. And then there is a second, more complicated requirement, which is this one. As you can see, it involves n, pi, and of course, the requirement is that this combination of n, pi, alpha, and x must be equal to 0 for all 1/4 alpha and for all vector fields x on the manifold. L of y, where y is a vector field, is as usual the Lie derivative along the vector field. We will see in some minutes how to say more transparent interpretation of this compatibility relation between n and pi, but for the moment it is this one. I'm sorry. So it is well known that in such a situation one can construct another Poisson tensor, pi prime, which is the composition between n and pi, and that thanks to the compatibility requirement, thanks to the fact that the torsion of n vanishes, this new tensor p prime is also a Poisson tensor, and moreover it is compatible with the old one, with the pi. And compatibility in this setting is very easy to describe it because it is simply the requirement that the sum between pi prime and pi is again a Poisson tensor. So one obtain a well-known geometrical object in the theory of not only finite dimensional, but in general integrable systems, also infinite dimensional integrable system. So a manifold M with the two compatible Poisson tensors, and this is called a bi-Hamiltonian manifold. The relation between Pn manifolds and integrable systems are quite easy to describe because, okay, we suppose that we have a Pn manifold, a Poisson-Nijenhuis manifold, and as a consequence of the fact that the torsion of n vanishes, one can show that the traces of the power of n, okay, here there is a coefficient 1/2k, which has not, doesn't have a particular meaning. It's also for ease of using in the following. But okay, the main point is that these functions hk satisfies this relation, and star acting on dhk is equal to dhk plus 1. And in turns, these relations imply the sometimes called Lennard-Magri relations. That is to say that the Hamiltonian vector field made with pi and the Hamiltonian hk plus 1 is the same as the Hamiltonian vector field constructed with the other Poisson tensor pi prime with the Hamiltonian hk. And and one can prove that the functions hk are in involution with respect to both Poisson brackets induced by the two Poisson tensors. And of course, if one wants an integrable system, then one has to check that the functions are not all in involution, but in a sufficient number, and they are independent, and so on and so forth. But the involutivity of the HK is the main link between the geometrical structure, PN manifold, and the theory of integrable systems. Okay, moreover, if we finally give a name to the Hamiltonian vector field xk, the Hamiltonian vector field with respect to the Poisson tensor pi, the old one, and the function hk, then the recursion relations on the differentials, the relation dhk plus 1 equal n star dhk, give rise to this relation with on the vector fields. The k plus 1 Hamiltonian vector field is simply n acting on the kth Hamiltonian vector field. And for this reason, n is sometimes called a recursion operator. Okay, before passing to the generalization, the PQN manifold, the PQN structures introduced by Stianon and Xu, let us see two examples of PN manifolds with the associated integrable systems. The first one is very trivial. We take free particles on the line, and so the manifold is simply m equal r to n. The coordinates can be called q1, etc., until the Pn. And we consider the canonical Poisson tensor pi and the following tensor field n. I will present it in the three particle case, but it is obvious how it is done in the general n particle case. So it's simply in this coordinate, the components of n are simply give simply a diagonal matrix, and on the diagonal we have p1, p2, p3, and then again p1, p2, and p3. It is very easy to check that it is compatible with pi and that the torsion vanishes. And so we have an example, first trivial, if you want, example of PN manifold. And it is called the canonical PN structure because under some assumption, under some specific assumption, a PN structure can be brought in this canonical form. And in this case, the traces of the powers of n are simply the sum of the powers of the pi. And so from the point of view of integrals of motion, we have the integrals of the free particle motion. Of course, these three constants of motion are equivalent to the well-known momenta P1, P2, and P3, which are obviously constant of motion in evolution. So a second and more interesting example is given by the open lattice. This was found. This PN structure was found by Das and Kubo in 1989, so the manifold is the same as in the previous example. It's simply R2n. The Poisson tensor is again the canonical one, and the difference is the tensor field n. Again, I will show it in the three particle case, but it can be easily guessed the general form. So the diagonal blocks are the same. Then we have in the northeast part a constant block with 1 and -1, and in the left lower block we have the exponentials. Again, it is compatible with pi and with Nijenhuis torsion, which vanishes. And so we have a second example of a PN manifold. And in this case, the traces of the powers of n are interesting functions. They are in the usual integrals of motion of the open total lattice. For example, H1 is simply the total momentum, H2 is simply the energy, and so on. And the other integrals of motion, as far as I know, they do not have a clear physical interpretation. So we have just noticed that the involutivity of these functions can be seen as a consequence of these recursion relations on the differentials. For the object we are going to introduce for the Poisson quasi-Nijenhuis manifolds, these relations do not hold because the torsion does not vanish. And so at the end of the talk, we will see that one needs additional assumptions if we want to prove that the functions are in involution. So we can define Poisson quasi-Nijenhuis manifolds. I will put in I put in red the differences between the old notion of Poisson Nijenhuis manifold and the new notion of Poisson quasi-Nijenhuis manifold. First of all, in addition to the manifold, the Poisson tensor pi, the tensor n, we have another object, a three-form phi. Pi is again a Poisson tensor, so and pi is a Poisson manifold. N is a 1-1 tensor field. As we will see, its torsion in general is not zero. And the requirements on these geometrical objects are the following. Like in the PN case, we want the Poisson tensor pi and the tensor field n to be compatible. There is no modification for the first requirement. The three-form I and phi, which is the simplest three-form that you can construct with the help of phi and n. So this is the definition. X, y, and z are vector fields on the manifold n, and I n of phi is constructed in this simple way. And so the second requirement is that this three-form is closed. So not only phi is closed, because there is also the requirement at the beginning that phi is closed. Not only phi is closed, but also I and phi. And then, as I already told you, the torsion of n is not in general vanishing, but it is in some sense controlled by the Poisson tensor pi and by the three-form phi, and this is the formula. Again, I of x wedge epsilon phi is the simplest one form we can construct with x, y, and phi, and it is simply the one form which gives, evaluated on z, phi of x, y, and z. So this is a one ix wedge y phi is a one form. We can act with the Poisson tensor pi on this one form. We obtain a vector field on the manifold. This vector field must coincide with the torsion of the n evaluated on x and y. So this is the definition of Poisson quasi-Nijenhuis manifold. first trivial remark is that if the closed three-form, if the three-form phi is not only closed, but it is 0, then the last requirement implies that the torsion of n is equal to 0. The compatibility between pi and n is already required, and so we have a Pn manifold. As a particular case of PQN manifold, we have a Pn manifold. It was expected. So in the paper where Stianone and Xu introduced and studied the concept of PQN manifold, they wrote explicitly that Poisson-Nijenhuis structures arise naturally in the study of integrable systems, and we have seen why. And it would be interesting to find applications of Poisson quasi-Nijenhuis structures in integrable systems as well. And we found such an application, and we showed that the integrability of the closed n-particle todal lattice and also its relation with the open todal lattice can be interpreted in the framework of PQN manifolds. To show this application, I need to present a general scheme to deform Pn manifolds into PQN manifolds. And to present this deformation theorem, we need two ingredients. So the first one is the following. We start from any tensor field n of type 1,1. It's not important that this torsion vanishes. And we can deform the Cartan differential using n and construct this operator dn in this way. So as usual, a hat on a vector field means that this vector field should be removed. And this Lie bracket, this n Lie bracket between vector fields is defined in this way. Alpha is a Q form, so dn alpha is, of course, a Q plus 1 form. It's easy to see that if n is the identity, this n Lie bracket is the usual Lie bracket between vector fields, and so this dn operator is the usual Cartan differential. And the second construction and the second object we need is the following. In this case, we forget about the tensor field n. We simply have a Poisson tensor on a manifold, and we can define with this Poisson tensor a Lie bracket between one forms in this way. And then we can extend this bracket to all forms on the manifold. Maybe it's a quarter to 3. Maybe I will skip these requirements. They are, how to say, very natural requirement in order to extend this bracket between one form and obtain a bracket between all kinds of forms on the manifold. One obtains a graded Lie bracket, which is sometimes called the Koszul bracket. And as I was saying before, Yvette Konzmann-Schwarzbach found a very nice way to describe the compatibility between the Poisson tensor pi and the 1,1 tensor field n. And she proved that pi and n are compatible if and only if dn is a derivation of this Koszul bracket in the sense of the formula which is written here. Okay, and so having introduced this dn operator and the Koszul bracket, we can finally state this deformation theorem. We start from a Pn manifold, we suppose that omega is a closed to form on M. It can be any closed to form on M. And as usual, we define the omega flat as a map from the tangent bundle to the cotangent bundle, which is defined in this way. And then if we introduce a new 1-1 tensor field n hat, which is simply n plus the composition between pi and omega flat, and we define the three-form phi to be dn of omega plus 1/2 of the Kosul bracket between omega and itself, then we can show that m pi hat n and phi is a PQN manifold. And as a corollary, if phi is equal to 0, that is to say that if omega satisfies this Maurer-Cartan type equation, then the form manifold is still a PN manifold. Okay, let us see how to apply this theorem to the Toda case. We start from the PN structure of the three-particle open Toda system, the one found by Dassendo Kubo, and we consider the two-form omega, which is simply in the three-particle case, but again, the n-particle case is very easy to guess. So it is the exponential of Q3 minus Q1 times dQ1 wedge dQ3. Omega is closed, and so we can apply the deformation theorem, and we can construct a PQN manifold with the same Poisson tensor and the new 1-1 tensor field n hat. It turns out that n hat is given in this way. Recall that in general n hat is n plus pi composed with the omega flat. And so here I put in red the additional part to, I mean, the black one is simply n, and the composition between pi and omega flat gives simply these two elements. One can check that the torsion of n hat is different from 0, so that the form structure is really PQN. It's not a Poisson-Nijenhuis manifold. The generalization to the n-particle case is obvious. And why this deformed PQN structure is related to the closed Toda lattice? Okay, because if one introduces the functions h hat k, which are up to a multiplicative constant, the traces of the powers of n hat, then h hat 2 is the Hamiltonian of the closed Toda lattice. So you see that we have the kinetic energy, the interaction between Q1 and Q2 and Q3, and in addition, the interaction between the first and the last particle. It's like saying that the particles are not on a line, but on a circle. This is why it's called periodic or closed Toda lattice. We can also deform the canonical PN structure. We can start from the canonical PN structure, which was in the three-particle case, again, the diagonal tensor n. And if we consider this omega, this to form omega, which is constructed with the help of a certain number of C-infinity functions on a single variable, Vij. So in this case, again, omega is closed. We can apply our deformation theorem, and the deformed tensor field n hat is this one. So remember that in this case, we start from the diagonal one. So we have in addition this block, northeast block, and this southeast block. With the suitable choices of the function Vij, we can see both the Pn structure of the open total lattice and the Pqn structure of the closed total lattice as the formation of the canonical one. From the physical point of view, we start from the free particle case and we can deform it and we can obtain or the open total lattice or the closed total lattice. In general, we obtain as H2, or maybe here it was better to write H hat 2, so 1/4 of the trace of n of the square of n hat. We have this function, so we have the Hamiltonian of n interactive particles on the line with unit mass, and the interaction can be any kind of interaction. Not only nearest neighbor interaction, because the second particle can also interact with the fourth one or the fifth one. It's very easy to see from both physical or mathematical grounds that H1 is in evolution with every HK, but in general, the functions are not in evolution. It's very easy to construct counterexample, and moreover, it would be, how to say, very unexpected that every kind of interaction gives rise to functions in evolution. And so for this reason, we decide it is very natural to introduce a subclass of PQN manifold. We called them involutive PQN manifolds. They are the PQN manifolds where the traces of the powers of n are in evolution. And as I was saying before, it's very easy to find examples of non-involutive PQN manifold. The PQN structure is too weak to, to ensure the involutivity. And so a natural problem is to find sufficient conditions for the involutivity of a given PQN manifold. And so I will almost finish presenting an involutive theorem. So we have a PQN manifold. Again, HK are the traces of the powers of n. To ensure the involutivity, we can suppose that there exists a two-form omega. It is the same notation as the one we used for the deformation, but it could be also a different one. So the requirement on omega is, requirement on the PQN structure is that the three-form phi can be factorized as dH1 wedge omega. And the second requirement is that if we evaluate omega on the Hamiltonian vector field xj, recall that xj is the Hamiltonian vector field with the unique Poisson tensor we have pi and the Hamiltonian hj. So if we compute the omega on xj and yk is the difference between the Hamiltonian vector fields and the vector fields obtained by acting on the x1, on the first one, by means of the powers of n. Okay, so the second requirement is that omega vanishes on such pairs of vector field. So in this case, we can show that the PQN manifold is involutive. That is to say that the HJ, HK, the Poisson bracket between HJ and HK is equal to 0 for all J and K. We can apply this involutivity theorem to the total case. We can start, in this case, omega is exactly the same form we used to transform the open case in the closed case, the Pn structure of the open case in the PQN structure of the closed case. And it is very easy to check that phi can be factorized in this way, but it's not so easy to show that omega vanishes on the pair of vector fields. Actually, in this case, we can show that a stronger condition, that omega vanishes on x and y k, where x is any vector field, but also showing that omega vanishes on the x, j, y, k is not at all easy. And so we have a geometric proof of the well-known fact that the closed Toda lattice is an integrable system. Of course, there are old and well-known proof, for example, using the Lax formalism. But this is another interpretation, a geometric interpretation in the setting of PQN manifolds.
Marco, excuse me. Marco,
yeah.
In the general definition, in the previous slide, omega is not supposed to be closed.
Okay, this is a good point. I didn't write that omega is closed, but maybe I need it. No, I don't think so. Okay,
well,
it's a good point.
I don't think so, because, well, it could be that with a non-closed omega, I'm not doing the computation, but I think that what you called I n phi could be closed without omega being closed. This is clear, but I don't know. Just to be sure that the definition this way.
I will check and I will tell you. I have to check the proof. I hope it's correct, and I don't need it.
For this proof, is not necessary to be closed.
Okay.
Okay.
But just to be sure.
Okay.
Okay, because in the example,
for the deformation, it is yes,
crucial. Yeah.
There are two different.
Okay, thank you, Igor.
Thanks.
Okay, no, thank you. So I'm just finishing. So a brief resume. We presented the general results showing how a PN structure can be deformed into a PQN structure by means of any closed to form, as Igor was saying correctly. We gave sufficient conditions for the involutivity of a PQN manifold, the theorem we have just seen. And we applied these results, both the deformation one, both the involutivity one, to the Toda system or to the Toda systems. And open problems, first of all, to find a better involutivity theorem with the conditions that are easier to check in the examples. And then apply our results to other integrable systems. For example, the rational Calogero model. I was mentioning it at the beginning, talking about my collaboration with Claudio. And for example, also to Toda lattices associated with the simple algebras. And then another possible line of research is to try to extend our results to the infinite dimensional case, to infinite dimensional systems. So thank you very much for your attention. And once more, happy birthday to Claudio. And thank you for being my friend.
Okay, thank you, Michael. I don't know how to do the applause here.
Well, there are. So thank you. May I ask?
Of course.
Yeah.
Of course.
Thank you, Marco. Thank you for your words, very kind words. And of course, it's a great pleasure to be your friend to me. Well, if I understand correctly, well, the interesting case is when deforming, say, a PN manifold you obtain a tree-form phi, which is different from 0, but was such that the torsion of n, of the associated n, is closed as well.
In which sense the torsion is
closed?
closed?
It can be that you have a Pn manifold, so a quasi Pn manifold, such that phi is different from 0, but the torsion of n is 0. This is
you mean the torsion of the torsion of the starting n?
Yes.
Yeah, okay. I start from a Pn manifold, so the torsion of n is equal to 0.
Yes.
But if phi is different from 0, then the torsion of n hat is not equal to 0 in general.
Yes, in general it is not, but could be.
Yeah, you are saying maybe there are particular situations in which
yes.
phi is different from 0 because okay, because the relation is this one. So it could be that it is a strong requirement because it must happen that this one form I of x wedge y on phi is in the kernel of phi for all x and y. Okay, but maybe it could happen. It can happen, I think.
Yeah, but if you start with a Pn manifold, you should this Maurer-Cartan type equation. I say.
Yeah, let me see.
Okay.
Point. Yeah,
yes.
This one.
Yes, this is the case. If you start from a Pn manifold, then you deform it, and if omega satisfies this Maurer-Cartan type equation, then you have a phi which is different from 0.
No, phi is equal to 0 in this case. Because,
in this case, yes.
This one.
Yeah.
Okay. Otherwise, otherwise you have this Maurer-Cartan equation, but let's say not homogeneous.
Yeah, the Maurer-Cartan equation in this case is the abstraction.
Yeah.
Okay, I'm a bit confused, but okay. Well, I was thinking about the possibility of studying the space of deformations of a Pn.
Okay.
With by means of Maurer-Cartan type equations or something like that. I don't know if you have been thinking about that or.
Maybe Igor thought about it. It's in any case, it's a good point. I think we should think about it.
Okay, we can.
We can discuss.
Yes, we can discuss about that in the future. Thank you. I'm very interested.
Pleasure.
It's kind of an old love with integrable systems. So thank you.
Well, thanks to you.
Any other question or remark? Okay, if not, let's thank Mike again for this talk.
Okay, I'll try to disconnect.